Mario is going to present on the location of micro-consolidation centers to reduce the social cost of last mile deliveries. Looking forward to your presentation.
Thank you. Thank you. Hello, everyone. We're going to go through this outline very briefly, like the introduction. I'm going to talk a little bit about the formulation, then the heuristic description, some applications that we got, and the conclusions, and finally the references of our work. As an introduction, we all know that the concentration of world population in big cities is increasing. We're expecting that by 2050, that increase would reach like around 66%. Also, carriers not only have to deal with the business-to-business dynamics, but they also have to do the deliveries to households nowadays that e-commerce has got so popular. And so measures like same-day delivery, free return policies are increasing significantly like the level of service that carriers need to provide. Public agencies nationwide here in the US have acknowledged that freight transportation is one of the key components for having more livable and more sustainable cities. But like, why do we bother with, for example, this type of research? Well, while we all benefit from getting our packages at home, there are some negative externalities associated with freight transportation. Why? Well, carriers are responsible, are the brokers between shippers and receivers, and they have to respond for the level of service of the entire supply chain. That's why they, for example, account for a big share in emissions since they use fossil fuel vehicles. And they also account for 17% of the congestion costs. When they double park, they use illegally the public space to actually consolidate deliveries. And that's like a big issue, especially when cities get more and more crowded. So that's why like this research like came to as an idea. The idea is like, okay, how can we help the carriers to do their job in a better way for everyone? And one of the possibilities is by introducing UMCs. A UMC, a Urban Micro-Consolidation Center, is any on-street or off-street space where all the deliveries within a certain radius are dropped and reconsolidated to be delivered by more sustainable last-leg modes like cargo bikes or hand carts and stuff like that. And as we can see, we can actually reduce the total time that trucks double park or that spend time finding parking because they don't have to do that anymore since they don't have to do all the stops in the last mile delivery. But the way that there is a lot of research about like the successful implementations of UNCs, but there is no much about how to use OR techniques to find, for example, an optimal location of UMCs, and that's what we're actually trying to achieve. We know that in general, there are like 4 types of agents involved in freight transportation: shippers, carriers, receivers, and policy planners. But here, we're assuming that the level of service for shippers and receivers remains unaltered, so the problem exhibits only a bi-level structure. We're dealing with the objectives of policy planners that try to minimize all the negative externalities and carriers that are trying to actually keep their operation profitable and minimize all the costs associated with it. After some considerations that actually you can see in our paper, we actually conclude that this problem can be reduced to be a single level common objective problem because the agents cooperate. Um, some of the assumptions that we actually include in our formulation are, for example, the geometry. We're using homogeneous blocks in a symmetric rectangular layout, as you can see in figure 1, inspired by Manhattan's layout. We're also assuming that the incidence area of a UMC is of 1 block away from the location of the UMC, as you can see in figure 2. And we're also adding an additional ring of blocks just for the sake of not having particular conditions on the boundary for some of the constraints. These blocks in the imaginary ring they don't affect like whatsoever the results of the formulation. They're just there to simplify things. This is just a grasp of the formulation of the big problem that we are trying to solve. As you can see, the common objective is to try to minimize the total vehicle miles traveled by all the trucks from all the carriers in the area. The variables that are under control of the policy planner are the location of the UMCs in each one of the blocks and the block assignments, because once we have the location of the UMCs, we can see the problem as the facility location. So we have to assign all the customers that are all the blocks that are not defined as UMCs. And that's where the TLVIJ variables do. And then we actually have to consider that problem or the variables that they are under the carrier's decision are feasible for each one of the carrier's feasible set, let's say, that is defined by the decisions of the policy planners. The variables under each carrier's decision are the cargo delivered, the blocks visited, and there are also like some constraints that are part of that set PK. I'm not gonna go into the detail of all the constraints there, but some of them are, for example, total demand fulfillment per block, etc. And specifically, I wanted to talk about the fact that we're using an approximation for the length of the tours of the trucks. We're using Beerwood's approximation that says that the length of the tour is proportional to the number of stops that the vehicle has to do in a specific area. And that constraint is the one that gives the quadratically constrained like nature to the problem. That's why we're calling it an MIQCP, a mixed integer quadratically constrained program. And it's because of these type of constraints. Um, the problem is like this problem is so big and complicated that Cplex struggles to actually find solutions within a reasonable time and with like a reasonable use of memory, even for small instances. So we actually had to come up with a heuristic based on the idea of the concept of complicating variables. Conejo, in his book of mathematical programming, is the name of the book, he defines a complicating variable as one that once it's giving a value, the big problem can be simplified into multiple sub-problems that can be solved independently. And in our case, all the location variables and the assignment variables are complicating because once we actually give them a value, the problem can be independently solved by each one of the carriers. In our case, or in his case, in the type of research that he formulated, he uses only continuous variables. So he can determine the value of the complicating variables by using a master problem sub-problem decomposition in which both problems like get feedback from the other and feedback to the other using optimality cuts and Lagrangian dual information. But in our case, since our problem is integer, we cannot use that. So we came up with this heuristic in which the value of the location for the UMCs is given is determined by this heuristic that just kind of computes the density of the number of stops around a specific block to see if it's like a good candidate for it to be a UMC. It is heuristic. It is a greedy heuristic because like every time we're going to locate a new UMC, it takes into account all the previous location that it has been doing. And that kind of is like one of the, not like the cons of this formulation, but it works well, as I'm going to show you now. In the applications, we deal first with the toy example. This toy example was useful because for this toy example, the classic Cplex for the original model could reach an optimal solution within a reasonable time. And as you can see in table 2, both the heuristic and the original model reach the same objective. However, the heuristic takes much less time in solving the problem, as you can see in the comparison of times for figure 3 for the different number of UMCs that we're trying to locate. But then we wanted to scale it up. So we went to we started generating multiple instances in a random fashion in a little bit more complicated layout with random demands. And what we did here is like, we wanted to evaluate the statistical significance of the differences. And we actually found out that for the location of the first UMCs, the heuristic is performing comparably well or even better than the original model. Why better? Because in this case, we couldn't actually solve the problem to optimality. We had to put a time limit of 6 hours per instance. And in some cases, the heuristic was reaching a much better level, a much better solution than the original model. As you actually increase the number of UMCs because of the greedy nature, the number of instances and the distance between the values for the instances of the original model tend to favor the original model even more, but not completely. And we can see that, for example, in this case, when we try to locate 5 UMCs, the maximum gap that we have between the solution of the heuristic and the original model is 7%, which is not like crazy, like terrible, let's say. We also, using only the heuristic because of the complexity, we also did a case study in Manhattan. The data and the sources and all the pre-processing for the data, you can find it in our paper. I'm going to share the link with you at the end. And where we brought all the data to account for the emissions, etc., and all the factors that we used in our model. And in the analysis of the results, I'm presenting you on in figure 2, the vehicle miles traveled, the social cost, and the marginal benefit of installing the next, like a next UMC, another UMC. And as you can see, this is type of like a Pareto situation in which like the first UMCs accounts for the highest benefits in the general problem. And for example, as you can see, the first UMC can achieve like a savings around $60,000 per year for the entire operation of the area that we considered in Manhattan. And even though we are not actually specifying all the characteristics of the UMCs, I mean, we're not giving any details about the operations of the vehicles, how are they going to do all the last mile delivery. These results can actually tell us like what is the maximum benefit that we could get, so that we could actually do like a feasibility analysis for the implementation of real UMCs with all of those aspects already like defined and considered. So I think this is important, and it shows like how like the great benefits of the initiative, for example, in the case of Manhattan. And as conclusions, I would just like to say that we think that this work represents a novel contribution in terms of the formulation and the creation of the heuristic that is very time efficient. The results of the case study are actually showing the potential of the UMCs as an initiative to increase the sustainability. And we acknowledge some of the limitations that we could probably like actually try to solve in further research, like the geometric assumptions or the treatment to the VRPs, that like the way we're actually computing the length of the tours, and the technical definition and characterization of a UMC that was like vaguely described and considered throughout the research.